Everyone. In this video, we are going to do some more hypothesis testing, and we're going to do hypothesis testing for the mean. We've been dealing exclusively with large samples. Most of the time we did not know the population standard deviation, but we were able to use the sample standard deviation to approximate the population standard deviation, and that works well for large samples. But now we're dealing with small samples, where n is less than 30, or we don't know the population standard deviation, which we haven't known that all along, and not knowing that is a little bit more authentic than pretending that you know it, because there aren't many situations where you actually know the population standard deviation anyway. So we cannot rely on the standard normal curve instead anymore for our calculations. So we can't use our norm.dist, we can't use our norm.inverse to do the things that we were doing to find our p-value or our confidence intervals. So instead, we're going to use a similar curve called the student t-distribution. But what you need to know first is that there's something called degrees of freedom, which is basically just the sample size minus 1. So that's going to be n minus 1. And so when you see degrees of freedom, just know that you're subtracting 1 from the sample size. So what are the big differences between the t-distribution and our standard normal curve? Well, a lot of things are the same. It's distributed with a mean of 0 and a standard deviation of 1, just like the standard normal curve. The area under the curve is 1, and it's symmetric about the y-axis, just like the standard normal curve. However, since there are only a finite number of different scenarios where our sample size is smaller than 30, there are only 30 ways that could happen, actually 29 ways that could happen, there's actually a table, a t-table distribution table, for each of those numbers, each of those degrees of freedom, so up to 29. And then after 29, it would just be a normal curve. So 30 sometimes is right on the cusp. So sometimes you'll see that we only use n is less than 30 for the t-distribution. Sometimes you'll see less than or equal to 30. When you're on the edge there, the t-distribution and the normal distribution are almost the same at that point anyway. And so the big difference is that the t-distribution has more padding on the edges, and that just makes it so that the probability is a little bit more on the outskirts of our distribution because we have a smaller sample size. There's going to be, we don't understand the variability as much for a smaller sample size than we do for a larger sample size. And so they just pad the edges a little bit depending on how large n is compared to our standard normal curve. And so it's more likely that you're going to have values that deviate from the mean. And so what we're going to use as we go through this, the couple of examples that we have here is, first, unlike the norm.dist function where all you had to know was the value you were interested in, the mean and the standard deviation, and then say that you wanted the cumulative thing, and it would do the rest for you in terms of it would change your value into a z-score and then find that value on the z table. The t-distribution only gives us the values on the t-table, and so we have to actually find the t-score first. So we're going to have to take our sample mean that we're given, x bar, subtract the population mean, or at least what we are assuming the population mean is, that's the null hypothesis, and then we're going to divide that by our standard error, and that will give us our t-score, and then we can plug it into this formula, t, comma, degrees of freedom, comma, true, and it will give us the area under the curve for the t-distribution up to that point. So the rest of it is just like it had been for the z-distribution when we were calculating z-scores that were less than or equal to a value. So let's go through an example, and hopefully this will make more sense as we go. But remember, the big difference here is that this is for small samples. So if you see n is less than 30 or n is less than or equal to 30, you should be using a t-distribution instead of using the z-scores or the standard normal distribution. So here we have a used car dealer that says that the mean price of a 2012 Ford F-150 Super Cab is $18,800. You suspect this claim is incorrect and find a random sample of 14 similar vehicles, and they have a mean price of $18,000 and a standard deviation of $1,250. So now we want to know, the rest of this hypothesis testing stuff is exactly the same. Is there enough evidence to reject the dealer's claim at a 0.05 significance level? So what we're going to do is we're going to write, just like we had been, our null hypothesis, H0, is that mu is equal to 18,800. So we haven't gathered enough evidence to say that this historically given value is incorrect. So that's going to be our default, that is mu. That's the mu sub 0 or mu naught that's in this formula. And then our alternative hypothesis is that mu is not equal to $18,800. And the problem did not specify greater than or equal to, greater than or less than. And so in this case, we're just looking for the claim to be incorrect, meaning it can miss on either side. So there's our null hypothesis and our alternative hypothesis. So now we need to calculate the p-value, and we're still comparing the p-value to our significance level. But the way we're going to calculate our p-value is a little bit different. First, I have to calculate t. So the things that I need in order to calculate t is I need to know what the mean is. So that's our x bar. I need to know what the claim is for the mean. I need to know what the standard deviation is, and I need to know what n is, sample size. Now, standard deviation in this case, I could skip right to, we know that s divided by the square root of n is also just the standard error, so I could have just written standard error and gotten rid of the sample size, but it's important to note when we're going to find our t-score from the t-dist function, we need to know what the degrees of freedom are, and that's going to be based on the sample size as well. So I just like to have that written down. Okay, I'm going to leave that there. All right, so x bar for this problem was 18,000. Mu was 18,800. The standard deviation was 1250. My sample size is 14. And so to find my t-score, t is going to equal, and I'm going to put that to the right here, t is going to equal, I'm going to make a formula here, it's going to be parentheses x bar minus mu, end parentheses, divided by parentheses standard deviation divided by the square root of n. And so that gives us a t-score of negative 2.3947. And this column just happens to be really skinny. If I expand that, there's more decimal places here. It doesn't matter how many you have in there. I just have negative 2.3947. So now that I have my t-score, I can go ahead and use my t-dist function. And so the probability that x bar would be, so this already less than our claim, so I'm going to say less than 18,000. That's going to be equal to, here, I'm going to put this in here, So now I can use my t.dist function. And so I'm going to put in, it says x, but that's really my t value, comma, degrees of freedom is going to be this value minus 1, comma, do we want this to be cumulative or not to be cumulative? And we want it to be cumulative because we want all of the area to that side. And that gives me a value of 0.016203608. Now this calculation that I did was for a one-tailed, a lower-tailed hypothesis test, but we are doing a two-tailed hypothesis test. And so I need to take that value and multiply it by 2, and that gives me 0.0324078, okay? This value is still less than my significance level of 0.05, so we need to decide whether we're going to reject or fail to reject the null hypothesis. In this case, since my p-value is less than my significance level, I will reject the null hypothesis. Which, what does that mean in the context of the problem? It means that the price, the average price of a 2012 Ford F-150 Super Cab is not $18,800. That's what it means. What's the only type of error that could have occurred here? Well, since we rejected the null hypothesis, a type 1 error is the only type that could occur.
Good afternoon.
So a type 1 error is the only type that could occur, which in the context of this problem would be that the average price is actually $18,800, and we said that it is not. Nobody's getting hurt here with this type 1 error, except maybe the dealer, who now is not going to get that sale because they are claiming something that you think is false. Okay? So in the next video, we're going to go through how to find the confidence interval for the sample of Ford F-150 Super Cabs. We'll find the confidence interval. The previous way we found confidence intervals is going to be a little bit different than this because, again, now we're talking about small samples. So we're going to have to actually calculate some stuff by hand and find a critical t-score. So we'll do that in the next video, and then we'll do an example where we are given the original data and then we're asked to do similar calculations.